Alright, so the next thing we're going to talk about here is temperature. We're going to start off talking about what it actually is. One of my things that I've noticed the most is a lot of people bring up temperature in different areas of science, and very few people understand what it actually is. Now, when dealing with different temperatures, a lot of the time people like to say that temperature, is how quickly molecules are moving and that kind of thing. While those types of definitions could be used, they're not really correct. Uh, because at the end of the day, the temperature relation to molecules moving actually depends on a lot of things. If you have molecules that are ideal gases moving throughout the air, you can say that the expected uh, kinetic energy they might have is, 3 over 2 times the Boltzmann constant times whatever the temperature is, which is where that argument comes from. However, if you confine them to move in 2 dimensions, that relationship fundamentally changes. If those particles are allowed to interact with each other, that argument fundamentally changes. And it's possible to have particles that can even have things like negative temperatures. And the question is, if you have particles that have negative temperatures, how much kinetic energy do they have? Do they have a negative kinetic energy? That doesn't make any sense. Right, so there's lots of exceptions to associating temperature with the movement of molecules. What we're going to do briefly here is we're going to talk about how temperature is actually defined. Now, you're not going to be expected to derive anything like this. It's just added for the sake of completeness. Now, dealing with temperatures is actually relatively straightforward. There's only one observation that's used to, or sorry, two observations that's used to deal with this. Observation number one is that your systems are going to evolve to the state they're most likely to be in. That doesn't seem like too much of a stretch, right? If you got a 1% chance of being in a particular orientation and a 99% chance of being in a different orientation, you're probably going to be in that second orientation there. When dealing with systems of molecules, it's not like 1% and 99%. You know, you might have a 1 in 10 to the 24 chance of being in one type of state, and basically 10 to the 24 out of 10 to the 24 of being in the other state. So the probabilities when dealing with things like atoms and molecules are actually ridiculous, so you pretty much are always in the most likely state. The second observation, the one that really defines temperature, is as follows. I have two objects with different temperature, a hot one here at T1 and a cooler one here of T2. And I bring them together and allow them to interact thermally with one another. You might ask yourself, well, what happens to them? And what happens to them is relatively simple. Uh, these two things here, they equilibrate over time. In other words, they evolve over time to their most likely configuration in which they have the same temperature. We'll call it T3. This here is pretty much the only thing that is truly used to define temperature. That's it. If you bring a hot thing and a cold thing together, they reach an equilibrium temperature with one another. Right? It's not super complicated, but you can work through it. Now, mathematically speaking, this leads to a very particular set of or a very particular context for temperature. Now, I'm going to show you an equation here. It is not quite the one I would use if I was doing this in a pure physics class, because I wanted temperature to be on the numerator of the fraction here. But the idea behind temperature is if you use this definition, which is what you see, temperature becomes a comparison to the rate of change. That's this little weird looking d thing of the amount of energy internal to your system divided by the change in the entropy. In other words, it's a rate of change that compares energy to entropy in a system. And this mathematically comes out of the laws of thermodynamics, right? Like, that's pretty much it. If you're dealing with the laws of thermodynamics, basically the law that states that entropy always increases just simply says that systems evolve into their most likely state, because entropy and probability are directly related to one another. Right? And this definition of temperature simply comes from this observation up at the top. Now, looking at energy as a rate of change means you can have a lot of weird things. It is possible for you to have a negative temperature in Kelvin. Right? A lot of people say you can't go below absolute zero. You can. To have a negative temperature here, all you need to have is a system in which entropy goes up, energy goes down. Or alternatively, if energy goes up, entropy goes down. Now, systems with negative temperature are very hard to come by. Typically speaking, if you have a system and you add energy to it, you're going to increase the entropy, because it's like having a box full of marbles. If you shake the box full of marbles, adding kinetic energy to it, you're probably going to increase how mixed up they are, increasing the entropy. If you increase energy and entropy, you have a system that has a positive temperature. There are some systems you can construct that have negative temperatures. If you've ever seen one of those toys, uh, I don't know if this is just me, but there's a little toy that has a little cardboard cutout, and inside the cardboard cutout, there's little tiny holes cut into the cardboard cutout, and inside the thing, there's little tiny marbles. Now, in this type of system, it is possible to shake the marbles around and have them actually fall into the hole. And if you can do so in such a way that increasing the energy of the system reduces its entropy, you have a negative temperature system. Now, if you don't believe me, it's a published science article. There's a variety of pop science outlets for it. So if you're on the internet, this is actually a pretty good explanation of it. Uh, but the idea is the reason why you can have this negative temperature is because temperature relates changes in energy to changes in entropy. Right? And this actually gives a nice low-level explanation of how it works. Oh wow, they drew those marble things way better than I did. Yeah, so basically you can have a set of hills and valleys in which you can have the system uh, reach a state in which, energy is increased and entropy is decreased. Now, the general idea behind why we're introducing is this is actually going to be very, very useful for predicting the behavior of molecular systems. Now, for the purpose of this section, as this is just an introduction to temperature, for this section we're actually just going to talk about converting between the different scales, as well as dealing with finite changes in thermal energy. Eventually we'll be talking about how temperature can be used to predict states of different likelihood in all sorts of different systems. And the reason we can determine the likelihood of different things is because it's possible to relate temperatures, energies, and entropies directly relate to probabilities. So you can find all sorts of stuff, such as how likely different atoms and molecules are to bind together, how likely different chemical processes are, with a very quick comparison between energy, entropy, and temperature.